Hello everyone and welcome back to Math with Vanch. I am Vanch and I will be teaching you math, obviously. So we will be continuing with the AP Calculus curriculum, and today we will be covering the properties of limits and how to solve for limits algebraically. Now if you're ready, I am too. Let's get started. So for the different properties of limits, you can see that there are 5 main properties that you have to memorize. There's the scalar multiple, the sum or difference, the product, the quotient, and the power properties. And they all basically say that if you have a function or an operation inside the limit, you can move that operation outside the limit and apply the same operation to either the two limits or just a singular limit. For example, if we have the limit as x approaches c of b, which is just any constant, times the function f of x, that's the same thing as if you took b times the limit as x approaches c of f of x. Same thing in the sum or difference property. We can see that the limit as x approaches c of f of x plus or minus g of x equals those two basically broken apart, like the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. And you can see this within all the properties. You can basically see that if you have two functions, you can basically just break them apart and apply the same operation. Also in the product property, if f of x and g of x are multiplied within the limit, you can just multiply the limit of f of x times the limit of g of x and get the same answer. Same thing with quotient. The limit as x approaches c of f of x over g of x equals the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. And finally, we have the power property, which says the limit as x approaches c of f of x to the power of some number n equals the limit as x approaches c of f of x, and all of that to the power of n. So a common pattern you can see is that basically whatever operation you do within the limit, you can take outside of the limit, and this makes it pretty intuitive and easy to remember. Okay, now let's get into how to solve for limits algebraically. So there's 4 different cases or steps, if you want to think about it that way, for solving limits algebraically. The first case or step is just direct substitution, which is just plugging in the x value that x approaches into the function. The second step or case is to factor, simplify, and then direct substitute. And then the third case is to rationalize and then direct substitute. And the fourth case is using trigonometric identities or expressions. So let's look at each of these separately. So we have these two examples over here. We have the limit as x approaches 2 of x cubed and the limit as x approaches 0 of 2x minus 1. Now these are two cases where we can just directly substitute. And direct substitute basically means that as x approaches 2, we can just plug in this value of 2 into the function. So if we do that, if we plug in 2 for x, we get 2 cubed or 8. Now for the second one, if we just plug in 0, because that's what x is approaching, we can do 2 times 0, 2 times 0, and then minus 1, which equals 0 minus 1, which would be negative 1. So why does this work? Well, this only works if the graph is continuous and doesn't have asymptotes. So what does that really mean? Well, we will get into this in a later video, but for now, what you really need to know is that all polynomials would be continuous and most trigonometric functions will be continuous except for a few, such as tangent, cotangent, secant, and cosecant. So basically polynomials are functions that have x and then to a degree, such as x to the fourth plus x to the third plus x to the x squared plus x and then plus 1. That would be a polynomial, and all polynomials are inherently continuous. And this also means that x exists for all real numbers. And this only works if the function is continuous at this point right here. Now here we have the second case, which is the factoring case. Now when do we have to do this case? We have to do this case if we plug in this value that x is approaching into the function and we get the indeterminate form. Now what is the indeterminate form? So the indeterminate form right here. This is the form 0 over 0. And in this case, if we get this case, we know we have to factor. So let's try plugging in values. So let's try plugging in 0 into this equation. We can see that we get 0 squared, which is 0, plus 3 times 0, which is 0, and then over 0. So this equals that. So we know we have to factor over here. And same thing for this example, we get, if we plug in -1, we get -1 squared, which is 1, minus 1, over -1 plus 1. We can see that this also equals 0 over 0. So now if we want to solve this, we would have to factor. So let's erase this and let's start factoring. So this one on the top, we can factor out an x, and then we would be left with x plus 3 over x. And then we can cancel out these x's right here, and we're left with x plus 3. Oh, and another thing, when we factor, we have to remember to keep the limits. I actually forgot to do that just now. So this would be the limit as x approaches 0 of this, and the limit as x approaches 0 of x plus 3. And here we can see we can just direct substitute because this is continuous for all real values of x. So if we plug in 0 into this function, we get 0 plus 3, which is just 3. And that would be our answer for this right here. Now, for the second one, we can factor out the top. We know x squared minus 1. We can factor that to x minus 1 times x plus 1. Oh, and the limit. Here, I'll just erase this. The limit as x approaches -1, and then this, x plus 1 times x minus 1 over x plus 1. And then we can cancel out this, and then here down we're left with the limit as x approaches -1 of x minus 1. And then here we can just directly substitute because this is a function that is defined for all real values of x. So if we plug in -1 right here, we get -1 minus 1, which is -2. And that's how we solve limits using the factoring method. Now we have the third method, which is the rationalizing method. This method we use if we plug in the value that x is approaching and into the function and we get the indeterminate form, and there's a radical symbol or a square root sign in either the numerator or the denominator. So we can see that the second case has been fulfilled. There is a radical symbol in the numerator. And what about the indeterminate form? So we can see that if we plug in x equals 4, we get root 4 plus 5, which is root 9, minus 3 over 4 minus 4, which equals 3 minus 3, which is 0, over 4 minus 4, which is also 0. So this is the indeterminate form which we have reached. So now we know we have to rationalize. So to do that, we will take the limit as x approaches 4 of this, x plus 5 minus 3 over x minus 4. And we will be multiplying this, so these two are equal. We will be multiplying this by the conjugate of whichever side has the radical. So here we know that the numerator has the radical, so we will be multiplying by the conjugate of the numerator. Now, a conjugate is basically the same exact expression, except the sign in between is just flipped. So like, if we multiply here by the conjugate, we can see it's the same expression, root x plus 5 minus 3. But this sign in the middle, which is a negative sign, we would flip it to a positive sign right there. And then multiply both the top and bottom by it. And we can do this because multiplying something by the same number, top and bottom, is the same as multiplying by 1. So this is why we can do this. So now in this case, we get, now we can see that this is in the form a minus b times a plus b, which is equal to a squared minus b squared. And this is a algebra 2 concept, which is prerequisite knowledge, and you are expected to know this before you take calculus. So we will be using the same idea here. So our a in this case would be root x plus 5. So this equals root x plus 5 and then squared. So we would get rid of the square root symbol. So we just have x plus 5 minus b squared. Our b in this case would be 3. So we would just do 3 squared. So 3 times 3 minus 9 on the top. And on the bottom, we can just leave it as the expression x minus 4 times root x plus 5 plus 3 right here. And now if we simplify the top, we see that we get the limit as x approaches 4 of x minus 4 on the top, because x plus 5 minus 9. Plus 5 minus 9 is the same thing as minus 4. So x minus 4 on the top over x minus 4. I forgot parentheses here. X minus 4 times root x plus 5 plus 3. And then these cancel out. And we are left with the limit as x approaches 4 of 1 over root x plus 5 plus 3. And now if we plug in 4 right here, we can see that we get root 9 because 4 plus 5 is 9. So 1 over root 9 and then plus 3. We know root 9 is just 3. So we get 1 over 3 plus 3, which is 6. And that is our answer. So the main idea of this is to basically multiply by the conjugate only when you reach the indeterminate form and if there's a radical symbol either in the numerator or the denominator. Now for the trigonometric approach to solving limits, we have these two functions graphed. We have f of x equals sine x over x and f of x equals 1 minus cosine x over x. Now we want to find the limit as x approaches 0 for both of these functions because that's something that shows up a lot when we're solving for trigonometric limits. Now for both functions, we can see that x is not continuous at 0 and does not exist. This is because if we plug in 0 to both these equations, we get the form 0 over 0, which is the indeterminate form. Now here we can see that as x approaches 0 from both sides, y seems to be approaching 1 right here. So because of this, we can say that the limit as x approaches 0 of sine of x over x equals 1. Now if we do the same thing on the bottom right here, we can see that as x approaches 0 from both sides, f of x seems to be approaching 0, even though it's not actually 0. So because of this, again, we can say that the limit as x approaches 0 of 1 minus cosine x over x equals 0. Now, these two limits are very important to memorize, and because they show up a lot in trigonometric limits. And these two are really the only limits that you should memorize for the AP Calc exam. Now, let's do some example problems. Now, suppose we had the limit as x approaches 0 of sine of x over 5x. Now this would, if we factored out 1 over 5, we would be left with the limit as x approaches 0 of 1 over 5 times sine x over x. And this is the same thing because if we multiply across, then we can see that 1 times sine x is just sine x, and then 5 times x is 5x. So it's the same thing. And from our properties of limits, we know that if we have a constant multiplying the function, we can just bring the constant outside. So that equals 1 over 5 times the limit as x approaches 0 of sine x over x. And we know that this is just 1 right here because we found that in the graph. So that equals 1 over 5 times 1, which equals 1 over 5. And that would be our answer to this limit right here. Now let's take another limit using the other equation that we found. And that was with 1 minus cosine x over x. So let's do the limit as x approaches 0 of 3 times 1 minus cosine x, all of that over x. And now we can just factor out a 3 like we did in the last problem. So the limit as x approaches 0 of 3 times 1 minus cosine x over x. Now again, we can split this up into, not split up, we can bring this 3 outside because it's a constant multiplying the function, and then we would be left with 3 times the limit as x approaches 0 of 1 minus cosine x all over x. And we found that this is just 0 as in the graph. So now we know that this is just 3 times 0, which is just 0. So this is your answer to this limit right here. This equals 0. And that's basically all you need to know for the trigonometric functions. Just make sure you have these two main limits memorized. Now that is basically all you need to know for the properties of limits and how to solve for limits algebraically. In the next video, we will be covering the intro to continuity and what it means for a function to be continuous. If you're enjoying my videos and finding them helpful, I'm glad. And if you have any feedback, please let me know in the comments so I can make them better. Until then, I'll see you for the next video. Bye-bye.